dependencies. And the speaker is Christopher Scaffidi from Oregon State University.
Hello. You can see my speaker's notes here. Right. So this work is on behalf of myself and Andrew Dove, who's from National Instruments, and my student Tahmid Nabi. And as a professor at Oregon State University, I often get these requests from health science researchers for help with making apps. And they often ask me, can you send a student over to help? And I tell them, I'm fresh out of Minions. I can't send you any. So this got me to wondering, why are so many scientists asking for help with making these apps? They seem relatively simple in most cases. They want to collect some data off of a mobile device, send it to a database on the cloud, and then display the results in a browser. So these mobile cloud web applications seem relatively simple to me. Why is it so hard? So that got me thinking, what could we do to make it easier so that maybe scientists could create these apps for themselves? So to give you a flavor for what's involved in making such an app, here's some little pieces of code of one app that I did make for transferring noise and GPS monitoring to the cloud. This little piece of data, this little piece of code right here is part of a larger application, several hundred lines long, that exists in the mobile device. And then that code over there is it runs on the server. It receives that data and stores it in a database. And then this code down here, JavaScript, calls up the database via the server in order to get the data. And one problem that frequently has come to my attention when teaching students how to develop this is the problem of hidden dependencies. So these pieces of code pass data to one another, and they depend on one another for data to be passed in certain ways, for instance, with certain parameters. And none of that is made explicit anywhere in the application's code, because there's 3 programs, and they refer to one another through these variable references. But there's no single program that can be analyzed in one piece. This can also occur even within one particular program. For instance, you can have dynamic dependencies in JavaScript where at runtime you register functions to be called in the event of certain situations or events or inputs, and then that in turn can lead to a cascade of other events. So these dependencies are often very hard to trace. And this is what cognitive dimensions refers to as a hidden dependency, because these pieces of code depend on one another in ways that are not made explicit by the notation. And currently, the best method available for making these clear is commenting, what cognitive dimensions refers to as a form of secondary notation. Of course, the trade-off, and cognitive dimensions is really all about talking about trade-offs, so the trade-off is you have to keep these comments up to date. Maybe there are other alternatives for JavaScript in particular. For instance, promises are being introduced as a way of making asynchronous calls more explicit. But this really doesn't do anything to make the calls between, say, the app and the cloud explicit. It's really only for JavaScript within a particular program. So this got me to thinking, and this was about 2012 in the fall, what can we do in order to make these dependencies more visible? And my first thought was, let's make something like the Google Web Toolkit, GWT, where you annotate an object-oriented language with types and Java annotations so that a compiler can automatically break apart one program and deploy pieces. So GWT can do code, can deploy some to the cloud and some to the browser as JavaScript. And I was thinking, well, I'll enhance this so then, now it can also generate JavaScript. But then I realized, although this adds a lot of role expressiveness because you can have an API for each important thing, it actually doesn't do a great deal for making those dependencies visible, because you still have to visually trace through the code in order to figure out what calls what and what depends on what. Or as in the case of Tracy's example, you may be looking at the outputs, but the problems are actually related to your inputs, and you have to visually trace through the code to figure that out. And in addition, now we'd have all of these object-oriented abstractions that my poor scientists would have to learn. And that's what cognitive dimensions refers to as a steep abstraction gradient. So I figured I needed to keep thinking. And the next thing I thought of was way at the other extreme. I thought, well, we'll make an English-like language, and you'll just express in one file in some sort of English-like notation what the whole system should do. And then some magic compiler will carve that up, turn it into JavaScript, and deploy it to the different devices. And so I thought about that for a while, and I realized, okay, it has a lower abstraction barrier and has all this nice English-like syntactic sugar. But on the other hand, you still have to visually trace through the program to see how the outputs relate to particular inputs. So I thought, okay, this is not good enough. And about March of 2013, I realized what I was really looking for is something where it was more visual, and like the components were represented as computations in little boxes or something with arrows. And I realized what I was looking for is something like LabVIEW. And that's when I invited Andrew Dove from National Instruments to collaborate, because his company makes LabVIEW. It's probably the most popular visual programming language in the world. And so he helped me to develop some ideas for what would this language actually look like. So this is a sketch in PowerPoint of one of the applications. I've been showing you a series of different use cases for different proposals that we've written for, home health monitoring, asthma monitoring. This one is for monitoring physical activity in for people who are taking nutritional supplements. And as we worked through how to express these kinds of things in PowerPoint, I found, now we really have made these dependencies visible because there's an arrow for each spot where a component depends on another component, regardless of whether it's in the browser or the cloud or whatnot. And the abstraction gradient is probably about the same as LabVIEW, which people supposedly can learn in somewhere less than a day. You can get going with LabVIEW. The downside of visual languages are well known, of course. Diffuseness and the verbosity of it is the key limitation because, it could just spread out and you're scrolling around trying to find stuff. So in order to assure ourselves this wasn't going to be a major problem, we made some scenarios based on the different health proposals that we had done and some scenarios that Andrew came up that were not related to health monitoring. And we made PowerPoint slides describing those programs and assured ourselves that we could express these programs in 1 or 2 slides. So having identified sort of what do we really want the language to be, we started creating what is now known as LondonTube. And here is a LondonTube program. It compiles and runs. Every 60 seconds, the Android records the acceleration as a scalar, the magnitude, sends it to the cloud, which stores it to a database. When the browser starts up, it asks the cloud, could you send me your stuff? And it packages it, sends it to the browser, and displays it on a chart. And we have about 80 different programs like this that do many various different things that we've used as our test cases. So how does it work? It follows, for the most part, structured data flow. Data flow is where a node is a computation, and it doesn't execute until its inputs are ready. And then at some point, then it reads its inputs, executes computation, produces its output, and that's called data flow. Now, structured data flow means that nodes can contain other nodes. For instance, a loop can contain a certain number of elements, and it'll run what's inside of it a certain number of times and then dump the results. So what LondonTube inherits from LabVIEW is structured data flow within each of these event handlers. So when you receive an event, structured data flow will execute. And it also inherits the Turing completeness of LabVIEW. So if you can compute it in Java, you can compute it in LabVIEW, and so you can compute it in LondonTube. But it goes beyond LabVIEW in that in LabVIEW, as with traditional languages, you'd have to make one program for the browser, one for the cloud, and one for the Android. And none of the dependencies among these would be represented. In LondonTube, those are represented with those golden arrows, and they actually follow an actor-based paradigm. So they're actually sending messages to one another. And when a message is received, it executes the corresponding structured data flow code. We also have a lot of other primitives. I won't go into the gory details. You can look in the paper, but we have nodes for reading sensors on the Android, nodes for storing and reading from the database on the cloud, and nodes for creating user interfaces on the browser. So after the scientist or other user draws this picture, which we call a back panel, or BP, in a browser-based editor, it saves to our server, and the user selects Run from a menu, and our compiler breaks that into pieces, and it converts each one of those pieces of the picture into JavaScript, which it then deploys at runtime directly to the cloud, runs it in memory, or onto the runtime that we have in the Android app, or when you fire up a browser and hit the server at a different URL, it will start executing the browser part inside of the browser, so you can display the output. And these different runtimes will exchange messages, those greenish-yellow lines, via JSON messages. So the programmer doesn't need to think about any of that. Now, we evaluated whether or not people could use this system. And in some sense, it's a formative evaluation in that it is a relatively small sample size, and it provided a lot of information to us about how we want to enhance this platform going forward. We also included a comparison condition with traditional tools. I had one grad student and one undergrad use traditional tools. They're CS majors. One grad student, one undergrad who are CS majors use LondonTube. And then two health science students, one grad and one undergrad, use LondonTube. And we gave them a programming task. All of the CS students had already taken a 10-week course that I offered on mobile and cloud development or an equivalent mentorship. One of the students was with me for mentorship for that same period. And all of the conditions started with a 3-hour tutorial. So the students who were using traditional tools reviewed all of my course notes, which I actually had pruned so that a lot of irrelevant stuff weren't included in the course notes that they had to review. They had 3 hours to do it. And then for the 4 who used LondonTube, I covered exactly the same topics: how to do a hello world, how to do a loop, how to send data, how to read from sensors, how to read from the database, how to display in a chart. We had 7 tutorials in 3 hours, and then they had a programming task. So the programming task was to read the accelerometer every few minutes, send it to the cloud, and then display it on a chart. Very simple task. In my opinion, about the same order of complexity as what Tracy asked her students to do, excepting that in my case, I gave them 4 hours to do it. The undergraduates could choose any tool that they wanted. Both of them chose to use Google App Engine for the cloud. One of them used the iOS simulator with an accelerometry simulation library for the mobile part, and the other used a real Android device. And then all the LondonTube users had a real Android device, and they used our server for creating their code. So none of the students using the traditional tools were able to finish it. I should say neither, okay? So neither of them were able to finish it in 4 hours. I myself have done this task. Before I did the experiment, it took me about 2 hours. And this morning, I timed myself again. I'm now 1 year more experienced with the tools and the language. It took me 64 minutes. And I didn't have any major missteps along the way. So I think that's about the fastest that you could use these tools to complete this little application. The LondonTube users all finished somewhere between 8 and 10 minutes. So just to give you some example of some of the problems that my students encountered with traditional tools, they spent a ridiculous amount of time registering sensor listeners, and it just wouldn't get right. And you know what, this morning when I was doing it myself, I didn't get it right either on my first try, and I had to debug it. And that cost me like 10 or 15 minutes. And then in addition, they had a lot of trouble passing data between the server and these other devices. And I heard the word dependency 3 times in Tracy's lecture. And that was clearly what they were struggling with here, dependencies between different asynchronous processes, the sort of thing that LondonTube handles directly. Now, I also kept track of what questions my students asked during this study. So when they were doing the tutorial, I actually answered the questions. When they were doing the task, I wrote down the question, and I only really answered it if they were asking for a clarification of the task. If they were asking for help, I let them do it on their own. So I found these guys who use the traditional tools, half their questions were about passing data between these concurrent processes or concurrent threads inside of the Android app. Something that was very similar between the two was choosing. So choosing which nodes to drag and drop onto your BP or choosing which APIs to invoke. So that was a common problem between the two, and it's actually one area that I had hoped we would be able to do better. So that's one area to look at in future work. In addition, after this study, we gave them a little survey with 12 questions in 4 different categories. They were Likert questions. How much do you agree with different aspects of the goodness of these systems? And then we asked overall about the usability and a rating of the speed of using the tools. And on every one of these dimensions, we found that LondonTube performed as well as the traditional tools, a little bit better. So we were able to combine these 4 using into scales, and all of them had Cronbach alpha of about 0.65 to about 0.9 or something like that. And dropping the least reliable item from the least reliable scale didn't change any of these results. And then we also just had their usability and speed of use. So obviously, with this small of a sample, we couldn't do a statistical test. So what we did instead was computed for each one of these categories the average given by our CS students with traditional tools. And then we counted how many ratings our LondonTube users gave that were above or below this average. And they outnumbered, I think they had 21 above, one below, and 2 of them were tied. So the ratings were far above average for LondonTube. So this study and this little prototype of our programming platform tells us a lot about the features that this has in common with other languages, as well as what it goes beyond in those areas. So there are a lot of languages where you can write a little program, whether it's in text or a visual program, and you specify, like, this piece of the code should run on a server here, and this piece should run over here. And ours is the only one that does both mobile cloud and browser, but there are others that are like just browser or just mobile and web. And our students had no trouble at all figuring out, how to annotate this code so that the right thing went there. So this tells me I don't need to make some sort of magical compiler like I had in the English-like language that can figure out what code goes where. It's okay to require people to label it. Another thing that it has in similarity with other languages is like Scratch and some other languages have these little primitives that say read from sensor. And the operator blocks until the read finishes. And you can do that in a data flow language because the rest of the program will just move along swimmingly. And nobody had any trouble with that. But my students with the traditional tools had a huge amount of trouble registering for asynchronous callbacks, which tells me this is a hot spot that we need to address in the professional programming tools. And then there's other related work which suggests areas that we can enhance it. Actually, my students are now using the system for, they've been using it for months for lots of little programs. And the things that I think are probably the most important right now is, first of all, discoverability. So you know exactly which nodes you want off of that palette. And when you look at a program, you can understand what the nodes do right away. And I also think we want to add some debugging support, especially as programs get bigger, because every IDE needs some debugging. And I think we have some good ideas for new types of debugging support that also will be beneficial for other data flow languages such as LabVIEW. So conclusions. First of all, there is a major potential to ease the creation of cloud mobile apps, particularly for health scientists. They need something that can help them with these simple little programs that just read from devices, send it to the cloud, and display the results in a browser. And this is one of many opportunities for DSLs in the health space. So I think that's a rich area for future investigation. Also, the students who used LondonTube took less time and were less confused by hidden dependencies. I think that we should focus on surfacing these hidden dependencies, not just in visual languages, but also in textual languages. I have yet to create a single mobile cloud web application that can fit on a single screen. LondonTube shows we can do far better than that. Thank you. Any questions you have, I'd appreciate.
Hi, Michael Koblenz, Carnegie Mellon. You mentioned that LondonTube has the potential of making it much easier to create these single-page applications in which you can display information from a sensor on a web page. But LondonTube, it seems like is a somewhat more general tool, useful for creating more kinds of systems than that. So I'm wondering if that's the kind of system we're particularly interested in creating, can we go one step further and make it even easier by further constraining what people can do?
You can always make things easier by constraining it more. In this case, we have a Turing-complete language that was very easy for people to use for this category of problems. Some of the ideas are already starting to make their way into LabVIEW, so I think we'll be able to address a larger population that way.
Thank you very much for your presentation. My name is Floos Erik from University of Tsukuba. So one guy in my lab is working on an Android application integrating a sensor device connected using Bluetooth to the Android tablet. I'm wondering how well does your platform integrate with these kind of native applications where you have to control sensors which are not covered by standard APIs?
Mm-hmm. Well, so we have nodes for read from GPS, read from accelerometer, and read from temperature sensor. So you also would like one read from Bluetooth. So my experience is that you have to write maybe about a dozen lines of Java code, put it into a class that can be loaded at runtime by the app, and then expose that as a node in the diagram. So depending on the details of your particular device, it probably would take no more than a day or two to add it to the language.
Okay, thank you.
You're welcome.
Let's thank our speaker, Christopher